All right, we're going to keep moving right along. Our next presentation is regarding the challenges and solutions for small systems regarding arsenic treatment. And the presenter's name is Lisa Miller from Golden State Water Company. She is a water quality engineer with over 10 years of water quality and regulatory compliance experience. She has a BS degree in biological sciences from the University of California, Irvine, and currently serves as the chair of the Distribution System Water Quality Committee. Thanks, Lisa.
All right. Good morning, and thank you for having me here this morning. I'll talk about arsenic treatment as we have it at Golden State Water Company. Okay, so just a brief overview of what I'll go over. We'll talk about the regulatory background behind arsenic. I won't go over it into too much detail because Eugene already talked about it. And we'll talk about available treatment technologies. I'll talk about Golden State Water Company's Artesia system and the groundwater wells that we have there affected by arsenic. And then I'll talk about the types of treatment that we use. We use coagulation filtration and adsorptive media. And I'll go over some of the challenges and issues that we have with those types of treatment and some pilot studies that we've done to address those issues. So the federal maximum contaminant level for arsenic is 10 micrograms per liter. It was issued in 2001 and it took effect in January 2006. This was lowered from the previous MCL of 50 micrograms per liter. The state of California also adopted a 10 microgram per liter MCL, and this one took effect in November 2008. The MCL was set based on health effects studies that show it to be a human carcinogen and also is linked to other health effects such as skin damage, neurological, and cardiovascular system problems. Arsenic can come from both natural deposits in the earth and also through man-made sources such as industrial or agricultural pollution, although it typically comes from, or it enters the water supply through the dissolution of those arsenic-bearing rock formations. And dissolved arsenic in water typically occurs in two main chemical forms. That's either the trivalent arsenite, or arsenic 3, or the pentavalent arsenate, also called arsenic 5. And that speciation plays an important role in arsenic's treatability. In neutral pH waters, arsenite has a net neutral charge and arsenate has a net negative charge. And it's that negative charge on arsenic 5 that allows the particles to be attracted to and to be or to readily attach to metal hydroxide surfaces and facilitates the removal. So conversion to the negatively charged arsenate is often a critical first step in the treatment process. And this conversion is accomplished by the addition of an oxidant prior to treatment, such as chlorine or permanganate. And this conversion does happen rapidly in water. As Eugene mentioned earlier, EPA lists 7 different best available technologies for arsenic. We have activated alumina, coagulation filtration, ion exchange, lime softening, reverse osmosis, electrodialysis, and oxidation filtration. Coagulation filtration and lime softening are not considered best available technology for systems smaller than 500 service connections, though. And just a quick note also, iron-based sorptive medias weren't part of the original best available technology list because at the time the arsenic rule was promulgated, there was limited performance research, although since then there has been plenty of research out there that shows that they are effective for removing arsenic. And I'll talk primarily about coagulation filtration and adsorptive medias since that's what we have in use at Golden State, and also they're probably 2 of the most common treatment technologies out there for arsenic. All right, so Golden State Water Company's Artesia system is located in Los Angeles County. It's part of our central district. It's 7 different water systems that we have throughout LA County. This particular system is in southeast LA County, and it serves portions of the cities of Artesia, Lakewood, and Hawaiian Gardens. We have a population of over 48,000 through 10,827 service connections, and it is primarily a groundwater system. We do have connections with neighboring utilities, but our groundwater sources are enough to supply the system, so it's all groundwater. We currently have 7 active wells, and 3 of those wells have treatment for arsenic. Those wells also do have co-occurring contaminants, including manganese and/or iron. So our main plant site that we have with the coagulation filtration process is our Centralia well number 6 plant site. This well and treatment plant were permitted and put into service in 2009. The well has arsenic. It ranges up to 41. The average is usually around 19 or 20. It also has manganese above the secondary MCL of 50, and it also has iron. It's not quite over the secondary MCL, but we do take both iron and manganese into consideration for this treatment process. And our permit requirement is to remove arsenic to below 80% of the MCL, although the average arsenic levels at our plant effluent are typically right around 5 or 6. So this treatment process involves the co-precipitation and adsorption filtration of iron, manganese, and arsenic. The first step, well water is chlorinated with sodium hypochlorite as it goes through the discharge line from the well, and that's to oxidize and facilitate the precipitation of arsenic, iron, and manganese. And then ferric chloride is injected after the sodium hypochlorite for additional arsenic coagulation and flocculation. Then the water passes through a static mixer to make sure everything's thoroughly mixed. And then the water flows through 2 dual media anthracite sand filters to collect those oxidized and coagulated particles in the media. The filter effluent is considered finished water, and at this particular plant site, it goes to a reservoir and then is boosted out to the distribution system. A few more specifics for the well. Centralia well number 6 has a design flow of 2,000 gallons per minute. It usually operates right around there. We have 2 horizontal pressure vessels that are 10 feet in diameter and 36 feet in length, with an available surface area of 336 square feet. Each filter is divided into 2 cells, cell A and cell B. It gives us a total of 4 cells. And the filter media consists of 18 inches of anthracite coal over 12 inches of silica sand and 31 inches of support gravel. With our 2,000 gallon minute flow, this gives us a filtration rate of about 3 gallons per minute per square foot. We dose chlorine to maintain a residual of about 1 milligram per liter at the plant effluent. So at the point of injection, it's usually around 5 milligrams per liter, which is prior to treatment. Ferric chloride is dosed in the 4 to 6 milligram per liter range, and this is sufficient to remove arsenic to well below that 80% mark. The media at this particular plant site is expected to have a 10-year life, and we have changed the media once since this plant has been in operation, and it was pretty close to that 10-year mark. In this process, the filters do need to be backwashed, so we have it set up to backwash every 24 hours of well runtime. The backwash occurs 1 cell at a time, and the backwash supply water is the effluent of the other 3 online cells. Each cell is backwashed for about 5 minutes, and then the backwash water is directed to 2 44,000 gallon backwash storage tanks and is allowed to settle. After settling, the clear decant water is recycled back to the headworks of the treatment plant and goes through the treatment process again. And then in our current operation, we have the settled sludge is hauled away every 2 weeks or so. One important treatment consideration for the coagulation filtration process is the waste handling. It does produce quite a bit of backwash water. And as I mentioned, we currently have the settled sludge hauled away. And anytime sludge is hauled away, of course, we do have to have a hazardous waste characterization done. We renew that hazardous waste characterization at least once a year. And we have had samples from that testing in the past that have come back over the state's arsenic limits, so it is considered non-RCRA hazardous waste. We have also had many samples that have not come back over the arsenic limits, but just out of an abundance of caution, we do have all of the sludge from this plant site hauled away as non-RCRA hazardous. A sewer connection is another good option for disposing of the backwash water. We do actually have a connection and a permit at this plant site to dispose to the local sanitation district. But the arsenic limit there is 3, and technically we should be able to meet that. But we also have a limit with the volume that we can discharge, and it's the volume that kind of limits us from being able to discharge our backwash water at this time. If we went that route, we would not be able to allow the backwash water to settle or concentrate at all. So we're looking into increasing the volume limits on that permit so that we can effectively use that sewer connection to dispose of the waste. So I wanted to talk about a pilot study that was done at the Centralia plant site. It was actually with 2 previous wells, Centralia wells 3 and 4. They have since been destroyed. But they were involved in a tailored collaboration project called Advanced Processes for Simultaneous Arsenic and Manganese Removal. The purpose of this study was to modify, demonstrate, and optimize an existing treatment process to simultaneously remove both arsenic and manganese. A secondary objective of this paper was to set out an efficient design process for other utilities wishing to implement the coagulation filtration process. So this study determined that ferric chloride could be easily added to existing oxidation filtration processes to successfully remove arsenic without negatively affecting manganese removal. The study determined appropriate ferric chloride dose, filter run times, loading rates, backwash handling, etc. And these 2 wells had raw water arsenic levels around 16. And with that, we found that ferric chloride doses between 2 and 4 could reduce arsenic down to 8. A dose of 6 was sufficient to remove it down to 5. And higher doses, of course, could remove arsenic all the way down to non-detect levels. But of course, with the greater ferric chloride doses, it does decrease your filter run times because of the higher amount of solids that are created. So to move on to the adsorptive media process, we have 2 wells in our Artesia system that currently utilize the adsorptive media. We have Hawaiian well number 1 and Messenger well number 1. These are 2 virtually identical wells that were drilled at the same time, perforated in similar zones. The treatment plants were built at the same time. Both of them were permitted and put into service in 2006. The Hawaiian well has an average arsenic level of 16, and the Messenger well has an average arsenic level of 21. Both of these wells also have manganese above the secondary MCL, so we have a separate set of filters to remove manganese before the set of arsenic filters. And average levels at the plant effluent here are typically non-detect. So in this process, we do again have co-occurring manganese. So the manganese is removed first. Well water is injected with chlorine prior to flowing through a set of 6 filters filled with manganese dioxide media for the removal of manganese. The water then flows through 6 pressure filters filled with a granular ferric oxide, which is an iron-based media. And the GFO media removes arsenic primarily through adsorption or partially through adhesion or formation, solid solution formation by reaction with ferric oxide ions. And then the effluent of the arsenic vessels is considered finished water, and at this plant site it does go directly to the distribution system. So this is our Hawaiian plant site right here. Both of the Hawaiian and Messenger plant sites have a design capacity of 600 gallons per minute each. And the manganese treatment consists of 6 pressure vessels in parallel. Each of those vessels has a 4-foot diameter and a 5-foot sidewall height. And then the arsenic vessels, again, we have 6 pressure filters. Each of those has a 4-foot diameter and an 8-foot sidewall height. And these vessels have a filtration rate of about 8 gallons per minute per square foot, which is towards the high end of what the manufacturer recommends for arsenic treatment. The GFO media does not need to be backwashed, but when arsenic breaks through, the media is spent and does need to be replaced. Backwashing can be done to kind of fluff the media and reduce compaction, but in our experience, we have found that it's not necessary. It doesn't necessarily help extend the media life. It doesn't really help with operational ease or anything like that. And the manganese vessels, on the other hand, of course, do need to be backwashed to remove those particulates. So we do have a backwash tank at these plant sites for that reason. One treatment consideration for the adsorptive media process is that it is typically single-pass media. I know there are some medias out there that can be regenerated, but I think they're less common. But with the granular ferric oxide, once the media is spent, it needs to be disposed of. Although it typically isn't hazardous, so at least there's no special hazardous waste handling requirements. And in terms of monitoring at these plant sites, we monitor arsenic in the combined effluent on a weekly basis. Once it reaches 6 micrograms per liter in the combined effluent, we monitor each individual vessel's effluent. And we can shut down individual vessels if needed if they get too high. Once the plant effluent reaches 8 micrograms per liter, we're required to schedule a media changeout. And if the plant reaches 9 micrograms per liter, then we're actually required to shut down. And in our experience, once the arsenic hits that 6 microgram per liter mark, it does increase pretty rapidly. So, by the time we have a change out scheduled, we're already having to shut the plant down because of high arsenic levels. Another issue that we've had with this treatment process has to do with the media life. We haven't been getting the number of bed volumes that we originally expected out of this media before we have to do a change out. In some cases, we've had as little as 12,750 bed volumes. And when these 2 plants first went into service, we were changing media out almost every 2 months. So with those more frequent media changes, that has, of course, added significantly to the operational cost of these 2 plant sites. And for that reason, because we weren't getting as many bed volumes as we expected, we had a pilot study done. It was Damon S. Williams Associates at the time. They did a study looking at different treatment alternatives. They looked at 2 categories of treatment alternatives, and the first was modifications to the existing adsorption system to see if we could improve the efficiency of the existing system. So we looked at hydraulic improvements because we found that arsenic was not breaking through at the same time in each vessel. Some vessels would break through a lot sooner than others. And so this looked at trying to improve the flow rates through the vessels to try to more evenly use that media. Vessel cycling was another option. This would allow some of the vessels to go ahead and break through while relying on other vessels that had not yet broken through to maintain arsenic below the MCL in the combined plant effluent. And then media would be replaced in individual vessels one at a time. But with that option, it could lead to almost weekly replacement of media in one vessel or another. Also considered lead lag vessel configuration, where this would, the lead vessel would be allowed to completely break through an arsenic while relying on the lag vessel to maintain arsenic levels below the MCL. But of course, with this process, it would require a second set of vessels as the lag vessels, which would be, or it'd have a significant capital cost associated. We also looked at pH depression because arsenic adsorption is improved at lower pHs, and of course considered other absorptive medias because there are several others out there. The second category of modifications that were considered had to do with modifications to the existing oxidation filtration system, including the addition of ferric chloride, residuals handling, and pH depression. With the addition of ferric chloride before the oxidation filtration vessels, that would convert us to a simultaneous arsenic and manganese treatment process, very similar to what we have at our Centralia plant site. We would, of course, have to take residuals handling into consideration because it would produce quite a bit more backwash water with that treatment process. And then at our Hawaiian plant, we actually did end up piloting the addition of ferric chloride prior to the manganese vessels, and did find that it would be an effective way to remove both arsenic and manganese, and has the potential for cost savings versus the current GFO media process. And then I did want to talk about one additional pilot study. This was done in Golden State Water Company's Hollydale system. It's very near the Artesia system at our Century plant. It was involved in the AWARF study, demonstration of emerging technologies for arsenic removal, volume 2, pilot testing. Our Century well number 1 was used to pilot test 4 different adsorptive medias. One of them was a proprietary aluminum-based sorbent by Engelhard. We also had granular ferric hydroxide by GEH. We had a iron-coated activated alumina by Alcan, and then also a high-porosity granular activated alumina. And these medias were tested under full-scale operation. We had 4 full-scale vessels, each operated in parallel, and each one had a different media in it so that we could really compare them side by side. And so the results from this testing done at our Century plant, it showed that the iron-based media, which in this case was the GFH and the iron-coated activated alumina, had a greater capacity for removing arsenic than the alumina-based media. And then of those 2 iron-based media, GFH performed the best because it had the highest iron content. The GFH media also treated a higher volume of water before initial arsenic breakthrough and a greater volume of water before arsenic exceeded the MCL. So this paper does provide design guidelines and operational criteria for full-scale systems for any utilities wishing to implement adsorptive media processes. So just a real quick wrap up. Coagulation and filtration and adsorptive medias are both great ways to remove arsenic from your source waters. Coagulation filtration successfully removes arsenic and other co-occurring contaminants such as iron and manganese all in one treatment process. And it does have waste residuals that need to be dealt with, of course. Adsorption is a fairly straightforward treatment process. It's easy to set up, and then you just deal with the media that needs to be replaced since it's single-pass media. And of course, the type of treatment and the success of treatment can vary quite a bit depending on site-specific factors and your source water quality. So pilot testing does help to determine what would work best for each individual plant site. And that's all I have for you guys. Thank you, and I'm happy to take any questions if you have any. We're just seeing, sure, yeah. He asked for our first treatment process where we have coagulation and filtration, we remove manganese along with the arsenic. He asked if we dose permanganate ahead of the treatment plant. And no, we just use chlorine and ferric chloride is all we use at that plant site. Yes?
Can you provide some insight into treatment costs for the
Yes, and unfortunately, I don't have specific treatment costs, but I can say, at least in our experience, the coagulation filtration, just because of the GFO media, it is very expensive media, and like I said, I mean, we've been changing it out much more than expected. So in our experience, we find that the coagulation filtration process does save a little bit on capital cost or operation and maintenance costs, but again, under our current process, we are also dealing with the sludge as hazardous waste, which that also gets very expensive. I mean, you know, we have to pay for hazardous waste hauling every 2 weeks, and then at the end of the year, we also have hazardous waste taxes. And so that's part of the reason that we're looking into the sewer connection. But yeah, I apologize, I don't have specific cost information on those two treatment processes.
Any concern due to the ferric chloride or corrosion control treatment or it's not suppressing your pH enough?
No, yeah, it hasn't suppressed our pH enough. I think, yes, he asked if there's any concerns with using the ferric chloride and corrosion issues associated with that, its use. And we haven't experienced that. Our source water has relatively high alkalinity, so the pH isn't impacted that much. I think the largest pH drop we've seen is about a half a pH unit, so it's really not significant.
If you chose to increase the ferric acid dose to get it down below the non-detect, I mean, that might be something that you would have to start worrying about would be the corrosion, I guess.
Potentially, yeah. If we did increase the ferric chloride dose and had much more of it, I mean, we would certainly have to look at that and make sure that it didn't decrease the pH too much, yeah.
And one of the things that you said, one of the reasons why you guys don't do it is because of the increase in sludge with if you've gotten out of non-detect, so it's kind of a size restraint, I guess. Is that why you don't treat down to non-detect?
Yeah, and you know, as I mentioned, our permit, we have to treat down to below 80% of the MCL, and of course, the more ferric chloride we use, the more residuals, more waste that we have. So it is kind of a balancing act for making sure that we do have safe, clean water. I mean, that's absolutely our primary objective, but we also want to balance the operational costs as well and keep those under control as much as we can. So.
I'm going to help you remember to repeat the question.
Thank you.
We have time for more questions if anybody has.
Yes?
The first treatment process you were describing, I think you said you were backwashing into a storage tank, settling out the sludge, and decanting off the clean water to the headworks. But you had the option of discharging to the sewer. What would you discharge to the sewer in that process?
So the question was, in the first process, the backwash goes to a backwash storage tank, and the current process was to recycle the decanted water to the back of the headworks of the treatment. And there's also a discharge to sewer option. And what are the considerations involved in why you do one versus the other?
Yes.
What would you take to the sewer?
Yes. So the difference with the sewer discharge is that we have to meet the sanitation district's limits for arsenic. And if we allow the sludge or the backwash water to settle out, of course, the arsenic gets concentrated in the sludge that settles to the bottom. And so if we discharged just that portion to the sewer, we would not meet the sanitation district's limits for arsenic. So we have to make sure that the backwash water stays evenly mixed to help dilute that arsenic concentration so that it doesn't settle at all, and we can discharge to the sewer and still meet their arsenic limitation. So it's kind of like dilution is the solution. Yes?
What's their MCL for discharging?
The sanitation district limit, it's 3 milligrams per liter for arsenic.
That was the limit for discharging to sanitary sewer.
Yes, thank you.
For those of you who are wondering why I'm doing this, we're recording this session for later use to make it available online, and so I want to make sure everybody who watches later knows what we're talking about.
Okay.
All right. Thanks very much, Lisa.
All right, thank you.